In this lesson, we're going to look at the last part of differentiation, which is how we can use what we've learnt about finding the maximum minimum value of functions and apply that to real life problems. So these questions are usually about shapes. So in 2D shapes, they'd be about finding a maximum or minimum area or perimeter, and in 3D shapes, they'd be about finding a maximum or minimum surface area or volume. So we're going to go straight into an example to see how this works. So if we have a read through this example and have a look at the diagram at the same time. So in this question, you're given a diagram. If you're not given a diagram, step one will always be to draw a diagram. So we've got an open box made from a square sheet of cardboard, 60 centimetres long, and we've cut a square X by X from each corner, and then we're going to fold up the sides to create this open cardboard box. So what it's worth doing is just adding some more information to this diagram. I know that the sides of the box are going to be, well, it's 60, take away 2 lots of X, because it's 60, take away this X here and this X here, and the base is square, so this is 60, take away 2x as well. And if we think about it, this is what we folded up to make the sides, so the height of the box is x. So there's the dimensions of my open top box. And if we have just a read through what we're going to have to do, we're going to have to find an expression for the volume of the box in terms of x, and then we're going to use differentiation to find the value of x, which will give us the maximum volume, and then find the maximum volume. So when reading these questions, you want to just have a look and see, is it about aerial perimeter in a 2D shape? Is it about volume or surface area in a 3D shape? And which of those things are we trying to maximise or minimise? So this one's about volume, and we're trying to maximise the volume of our box. So we're just going to make a note of that there. So draw the diagram if you're not given one. And the next thing we're going to need to do is to write an expression for the variable that needs to be maximised or minimised. So in this case, it's the volume that needs to be maximised. In terms of one variable only, that doesn't come into this example, but it will come in the next example. So let's start by writing our expression for the volume of the box. So the volume of the box is length times width times by height. So we're going to multiply the length times width times height together. So we'll get x times by 60 minus 2x squared. So we can see in this example our volume is in terms of one variable only, because it's only in terms of x. So that's part A. In part B, we have to use the gradient function to work out the value of x, which gives the maximum volume. So this is just like when we had a curve, finding the x coordinate of the stationary point, because the stationary point is where our function is at its maximum or minimum. So if we find the x coordinate of the stationary point, it's the same as finding the x value that gives the maximum volume. In order to differentiate this expression for volume, we're going to have to expand the brackets. So let's start by expanding those brackets. So we're going to have a double bracket expansion of 60 minus 2x. So we'll just do that. So now we've expanded the brackets, we can actually differentiate. Now this time, because I'm differentiating v equals, it's dv by dx, not dy by dx. Differentiate in exactly the same way. So in fact, just to give myself a little bit more room, Just going to move this over to the side because now I've differentiated. I want to find the value of x that gives the maximum value of volume. So in essence, I'm finding the value of x at the stationary point. So again, I can write at stationary point dv by dx equals 0. So I'm going to put my gradient function equal to 0, and I'm going to solve that equation. So I'm just going to factorise that, so it's going to make it easier to solve. So I can take out a 12, and then I can divide 3 by 12, and I'm going to put my x squared term at the front so I can do my factorising. And my solutions are x equals 30 and x equals 10. Now obviously if we had a negative solution we'd discard it because we can't have a negative length. Here we get two positive solutions, so which one do we actually want? Well, if we look at the length and width of the box, it's 60 minus 2x. Well, if I substitute 30 into there, I get 60 minus 60, which equals 0. So that gives me no length to the side of my box. So in this particular example, x equals 30 is not possible because it's not going to give me any length and width. So I'm going to take x equals 10. So that's the value of x that gives me the maximum value. But does it give me the maximum value, or does it actually give me the minimum value of the volume? Because we don't know at the moment whether this stationary point is a maximum or a minimum point. So the final thing we have to do is we have to justify whether the value of x we found gives the maximum or the minimum, depending on what the question's asked for. So in this question, it's asked for the maximum volume. So we're going to justify that x equals 10 does indeed give us a maximum volume, and to do that, we're going to use the second derivative. So if I define d2v by dx squared, so I'm going to differentiate my gradient function up here. So I get minus 480 plus 24x. So at x equals 10, the second derivative is going to be minus 480 plus 240. Well, I can see that that's going to be less than 0, so that tells me that indeed x equals 10 it's a maximum point on the curve, so that tells me that it's my maximum volume. So to finish off the question, x equals 10 gives the maximum volume. Now we just go back to the question, part C actually wants us to find that maximum volume. So we're going to have to substitute our value of x into our expression for v. So just to finish off then, our expression for v was x 60 minus 2x squared. So let's substitute in 10. So we get 10 60 minus 20 squared. So 10, 60 minus 20 is 40. So 10 times if we square 40, we're going to get square 4 is 16 plus 2 zeros. So I get 16,000 for my volume. And we're working in centimetres, so that's in centimetres cubed. Okay, so this was a reasonably straightforward example because when we found our expression for volume, it was already just in terms of one variable x. So we're going to have a look at an example where that isn't the case now. So for this question, we're not given a diagram, so we're going to underline key points and we're going to draw a diagram. So the first thing it's talking about here is perimeter, and then it says show that the area of the rectangle is greatest when the rectangle is a square. So actually, although it's given us some information about the perimeter, saying it has a fixed length, it's the area that it's asking us to maximise, because we want to know when the area is greatest. So again, in the question, it's worth noting, what are the two variables that we're working with, perimeter and area? Which one am I asked to maximise? So now let's draw a diagram. No, that's not a rectangle. Let's try and get a rectangle. So there's my rectangle. So what we're going to do is, on our rectangle, we're going to introduce two variables, one for the length, which I'm going to call x, and one for the width. And if we think about it, if we're trying to show that the maximum area is when the rectangle is a square, we're going to try and show that the maximum area is when x is equal to y, the length is equal to the width. So there's our diagram. Now we're going to write expressions for the area and the perimeter of the rectangle this time. So let's make a note again. The thing I'm trying to maximise is the area, and an expression for the area is just x times y. And an expression for the perimeter is 2x plus 2y, and I'm told that the perimeter has a fixed length. So I'm just going to put that perimeter equal to c, where c is just equal to a constant number, some fixed constant number that we don't know. So we've got an expression for an area and a perimeter, because that's what the question is talking about. And this is where we need to make sure that the variable to be maximised, i.e. the area, must be in terms of one letter only. And that's because I cannot differentiate x, y. I can only differentiate when I've got an expression in terms of just one letter x. So that's where the expression for perimeter comes in, and that's where this differs to the previous example. Because what I need to do, I need to substitute for x from my expression for the perimeter, so I get a in terms of one variable only. So let's just have a look at that down here. So we've said that a equals xy, okay, and we want in terms of x only. So we're going to use the perimeter expression to achieve this. So my perimeter expression was some constant is equal to 2x plus 2y. So if we rearrange this to make y the subject, that's going to give us, so if we take 2x on the other side and we divide by 2, we're going to get y equals c minus 2x over 2. So what we can do now is we can substitute this value for y into my expression for the area to eliminate y from my expression from the area. So I've got x times c minus 2x over 2, and if we just expand that bracket and simplify, I'm going to get cx over 2, and I've put the c in front of the x because remember c is just a number and we need to realise that when we differentiate, minus x squared. So there's my expression for area in terms of x only, so that I can now differentiate it. So differentiate the variable to be maximum and minimised, so that's the area in this case. So this time I'm finding dA by dx. So c is just a number, so when I differentiate cx over 2, I'm just going to get the number in front of the x, which is c over 2, and then that's minus 2x. So I'm trying to find the maximum value of the area, so I can write at a stationary point, dA by dx is equal to 0. So let's put dA by dx equal to 0 and solve. So first of all, I'm going to multiply by 2 to eliminate the fraction. So I get that x is equal to c over 4. at the stationary point or at the maximum area. But what this one has asked us to do is to not just find the value of x for the maximum perimeter, for the maximum area, but prove that is when the rectangle is a square. So we need to find the corresponding y for that x and show that the x and y are equal. So let's just do that. Let's just move this out of the way because I'm going to have to do that in a minute. So this is x at the stationary point. So let's find the y coordinate. We know from above that y is equal to c minus 2 x over 2. So that came from here when we rearranged the expression for the perimeter. So that was equal to c over 2 minus x, and if we substitute when x equals c over 4, we're going to get c over 2 minus c over 4, which gives me y equals c over 4. So if y equals c over 4 at the same time that x equals c over 4, that means that we do indeed have a square. So we know that the stationary point is where x equals c over 4 and y equals c over 4, so it is indeed when the rectangle is a square. We just need to justify that this does give us a maximum area. So we're not talking about a minimum point in this question, we're talking about a maximum, and we're talking about the area of the rectangle, so justify the maximum area using the second derivative. So we just need to find d2a squared by dx squared by finding the second derivative, so we're differentiating c over 2 minus 2x. Now remember, c over 2 is just a number because c is a constant, so when we differentiate that it goes to 0. When we differentiate minus 2x, we're just going to get minus 2. So in fact, in this example, the second derivative is minus 2, so is always negative, less than 0, so therefore our area is a maximum. Okay, so they're quite long questions, but we always need to follow through exactly the same steps. So here are the steps that we've used, and these are the steps that you're going to follow through for each of the questions. So before you have a go at the questions on a worksheet, I've got another question on the board, which I'll put up in a minute, and I want you to have a go at following these steps through. So I want you to give it a go on your own, and then I'll show you a full written out version so that you can compare or have a look at it if you're not sure at any point. So this is your question. I want you to use the steps from this previous slide and from your note sheet, work through them to have a go at this question. So pause the video now and try that, and once you're done, then you can start the video again and I will just show you the workings for this question.